We got one last family of functions to take a look at, and those are called lemniscates. Um, the way they're usually written, the formula would be something like this: r squared equals 4 cosine 2 theta. Now, in order to plot this, I've got to graph r equals, so I'm doing r equals the square root of 4 cosine 2 theta. Right? Again, I'm using a t for theta instead of a theta, just because it's hard to type a theta on the keyboard. Um, Now, when I think about how this works, I think about the graph of this thing, right? Now, if I didn't have the square root there, I'd have the graph of 4 times the cosine of 2 theta. That would go up as high as 4, down as low as minus 4, back up to 4, and the 2 is going to give me 2 cycles. So from 0 to 2 pi, I'm going to start at 4, go down to minus 4, up to 4, down to minus 4, up to 4. So that would be the cosine of 2 theta. Now when I take the square root of that, there's a couple things that happen. Right? First of all, the 4's get cut down to 2 because you're taking the square root. The other thing is that the negatives don't work underneath the square root. We're looking at real valued functions, so if you take a square root of a negative number, you're not getting a real output. So there's places here where the cosine of 2t is negative, and so when you take the square root, you don't get any result here. We don't get any real result. So there's just gaps in the graph here. So anyway, when I take a look here and I animate this and watch what happens as I go around, I'm going to start out here at an amplitude of 2, a radius of 2, and then as theta gets bigger, the radius will get smaller, come down to 0, then disappear for a while, and come back at 0 and go back up. Right? There's this part of the graph down here that's the square root of the negative, and it just goes away. So here we go. Let's take a look at it here. Oops, there's coming through the first part. Through this stretch right here, my theta value is out here somewhere, and there's just no r value that I can calculate. So there's nothing out there. And then suddenly we get back to calculating, and all right, I've got some positive r's. Make a little loop. It's kind of nice infinity symbol here. Right. Now, one of the things I'm a little leery of is that it's r squared equals this. So technically, this could be plus or minus. So I'm thinking, well, what would happen if I throw a minus sign in there? Maybe that would get me the stuff that I'm missing, or I don't know, what does it do? Actually, I can look at here and say no, because the minus sign is just going to turn this upside down, because that's after the square root. If I throw a minus in front of it, that's after the square root, and now I still end up tracing out the same thing. It's just that I do it on the negative side. So with the plus or the minus square root, I'm tracing out the same curve. Okay, plus or the minus square root. So yeah, there's lemniscates. There, various things. If you change this number here, you're going to change the amplitude. Let's go back to the positive here. I like it better with positive. So if I change that 4, I can, make it bigger or smaller. If I change that to a 5, it's going to be, radical 5 now for the maximum thing. If I want to get it all the way out to 3, I'd have to bring this up to a 9, right? So that square root of 9 is 3. The other thing that we look at as well is with a sign in here. So r squared equals 9 times the sine of 2t. And what happens now is that, again, think of this as a sine curve with period pi. So in 0 to 2 pi, you've got 2 cycles. But then when you take the square root, you'll lose the negative stuff because you can't take square roots of negatives and get real outputs. All right, you get imaginary outputs. So there's the graph, and you can see starting at 0, we climb out to amplitude. Well, in this case, radius 3, because I got a square root of 9 there, and then it comes back down to 0, disappears for a while. So all through the second quadrant there, from pi over 2 to pi, there's no radius obtained, so there's just nothing. And then it comes back in with positive there down in the third quadrant, and then nothing in the fourth quadrant. Right? So there's your. It doesn't look quite as much like an infinity symbol. This way it looks more like a propeller or something, but I don't know. These are lemniscates. We could. The books generally don't do this, but we could change that 2 to a 3 and see even more petals, I think. Right? You get this kind of thing. I don't know, I kind of like the look of that. To me, this feels like it's doing this and it's coming straight through like that, but that's not the way it's plotted. You plot this loop, then you don't plot anything for a while, then you plot this. Everything's positive here. Okay? What if I make that a 4? Okay. I can get as many propeller blades as I want this way, it looks like. All sorts of propeller blades. There's 5 of them. Oh, this is interesting because if you try getting a rose curve with 6 petals, it's really hard to do. But I can get 6 here very easily. And it's interesting because I'm leaving gaps. Right. There you go. I wouldn't call this a lemniscate. Lemniscates generally are only when you're talking with a 2 in here. That's what they're calling a lemniscate, these figure 8 things. Okay.